Okay, so basically, in this lecture here, I want to know what it means to say the metric space is complete. So by definition, a metric space X is said to be complete if every Cauchy sequence in X um, converges to a point in X. So, for example, let us consider the space of all continuous functions from the closed set AB to the set of real numbers. We want to show that this space is complete. In this case here, it's enough to show that if Fn is some sequence in the space, then it is Cauchy if and only if it converges to a continuous function f from the closed set AB to a set of real numbers. Now, if you recall from the previous lecture, we know that every convergent sequence is Cauchy. So that basically means that if Fn is a sequence that converges to a continuous function f from the closed set AB to R, then that means basically the sequence is going to be Cauchy. Now we have to show the converse. So here assume that Fn is some Cauchy sequence in the space, and then now because every Cauchy sequence has a convergent subsequence, you can consider the ordinary distance between the n term of the sequence and some real number a. Then by triangle equality, the ordinary distance between the n term of the sequence and the real number a is going to be less than or equal to the ordinary distance between the n term of the sequence and the n term of the subsequence plus the ordinary distance between the n term of the subsequence and a. Now in the limit, because the sequence is Cauchy, the ordinary distance between the n term of the sequence and the n term of the subsequence is going to be 0. And because the subsequence converges, so that means the ordinary distance between the n term of the subsequence and a is going to be 0 in the limit. But because the ordinary distance is non-negative, so that means basically in the limit, the ordinary distance between the n term of the sequence and the real number a is going to be 0. So the sequence is going to converge to basically a function, a continuous function from the set AB to the set of real numbers. Now let's consider another example. Here, in this example here, we want to know if a subspace of a complete space is complete. So consider the open interval 0, 2, which is basically a subset of R, and then consider the sequence 1 over k in X. Now it's not hard to show that this sequence here is going to be a Cauchy sequence, but the open interval 0, 2 doesn't contain all its limit points, because in the large k limit 1 over k is going to converge to 0, but 0 is not a limit point of a set. So that means the open interval 0, 2, which is a subset of the complete space R, is not complete.